Hey there, it's Modern Retro Tech, and today we are finishing our series of stream about Advent of Code. I will review my solutions for days 22 to 25, and we will revisit day 20 quickly to see how I in the end solved part 2 of that day. All solutions are with Rust, and then I guess in the end I will tell a bit about my experience solving everything with Rust this year. So let's start with our solutions. Yep, that's how the calendar looks in the end if you solve everything. So I hope I don't spoil it too much, but yep. Day 22. In essence, we have another game of Crab Combat here. Let me quickly close this stuff and show how our test input also looks and how our code looks for that day. So, in essence, you have some input. That's our input for player 1 and player 2, and then you have a game where you need to perform turns. You need to draw the top card of your deck, and then depending on if you have enough card or not, you can also branch out to another game. So in essence, you have multiple games there. For example, here in test arrangement, player 1 has 5 cards with 9 on top and 1 at the bottom. Player 2's deck has also 5 cards with 5 on top and 10 on the bottom. The first round begins with both players drawing the top card of the decks, 9 and 5. Player 1 has the highest card, so both cards move to the bottom of player 1's deck such that 9 is above 5. That's the first rule set, so you just need to simulate that, and then in the end you need to take the winning player's deck, and you need to go straight from left to right, multiplying each number by its reverse index, essentially. And you sum it, and that's your output for this quest. So, in essence, the rules are quite straightforward. So here I just say, okay, we have our solve function as usual. I start with my deck 1 and deck 2 that I parse from our input. Parsing function in this case is very straightforward. So we just skip the player IDs and we parse cards, converting them to U64. We use vec deck here because we will need to add both to the beginning and the end of the deck. So that's one interesting thing about this task. And then while neither deck is empty, we play rounds. Play round just takes a top card by popping the first element of the vec deck. And then if the top card of the player 1 is larger than top card of the player 2, we push both cards on the top on the first player's deck, otherwise on the second player deck. So with that, we get our answer, and it's exactly what was expected by the task. Now in part 2, the game becomes a bit more complex because we now need to create recursive rounds. So essentially, before either player deals a card, if there was a previous round in this game that had exactly the same cards in the same order in the same player's deck, the game instantly ends in a win for player 2. This is to prevent infinite games, essentially. Otherwise, this round's cards must be in a new configuration. The players begin the round by each drawing the top card of their deck as normal. If both players have at least as many cards remaining in the deck as the value of the cards they just drew, the winner of the round is determined by playing a new game of recursive combat. Otherwise, at least one player must not have enough cards left in their decks to recurse. The winner of the round is the player with the higher value card. So essentially, if you have enough cards to play recursive combat, you take the amount of cards that is equal to the value of the card you just drew from your deck, and then you play another completely separate game. And depending on who wins this game, the winner of that game is the winner of that round. So that's how it works. And here you can see another example input. So we start with game 1. The first draw 9 and 5. First player doesn't have 9 cards in his deck, so they cannot play recursively. So, but player 1 still wins because 9 is larger than 5. So he takes 9 and 5 and puts it in the end of his deck. Then they draw 2 and 8. 8 is larger, no recursion possibility, so player 2 wins, etc., 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 until they have this arrangement in the decks, and player 1 draws 4 and player 2 draws 3. Player 1 has 4 cards remaining in his deck after he drew the first one, and player 2 has also 4 cards, so they can play a recursive game. So another game starts with those cards. So first player has 4 cards because he drew 4. Second player has 3 cards because he drew 3. So that's the new decks on like separate recursive game. They play it normally. In the end, player 2 wins. The winner of game 2 is player 2. And that means that player 2 won the round 9 in the first original game here. So he takes 4 and 3 cards now, as we can see here. And then they continue play like that until eventually somebody wins. So we now need to essentially emulate that experience here. That was quite straightforward too. So it takes slightly more time to actually do that because of course we have more games, but there are like a couple of tricks you need to do. So we have function solve 2. We are again parse decks with the same exact function. We play game. And then we call calculate answer. So play game returns true if the first player won. It returns essentially a boolean and it returns a deck. So it returns a tuple of 2 values here. And deck is just a VAG deck of U64s, so of card values. Then if while decks are not empty, we create a round hash. So that's one thing, because we need to track if we already have experienced the same exact configuration of decks before. So that's why we just hash them. And we have a hash set of round hashes. And if it contains this round hash, according to the first rule that if we have exactly the same game configuration, first player wins, we just return true, meaning the first player won, and we return his deck. Otherwise, we insert the round hash into our round hashes hash set. Then we call play recursive round. Here we select first cards, we pop them from the VAG deck. If we have enough cards in our decks to play the recursive game, we create recursive decks by copying corresponding number of cards from our decks, and we call play game recursively. Otherwise, we just do comparison on top card 1 larger than top card 2. If it is true, then the first player won. We push both cards on his deck. Otherwise, on the second player's deck. And then if some deck is exhausted, so if first player's deck is exhausted, then we know that the second player won and we return their deck. If the first player won, we return their deck. So that's essentially that. One function that we need to define is dex hash, because by default we cannot just call hash function on a VAG deck. So in Rust, there is a bit of a complexity with how you hash stuff. You need to use this default hash thing. So that's why we have a bunch of, imports here. So we take this default hasher from HashMap, and we take hash and hasher traits from std hash that we need to actually hash those VAG decks. So we create this thing, we then can call hash, and then we pass a mutable reference to this hasher, and then we call finish, and that actually returns as a hash. So we do it with both our decks, and then we just take a hash of a tuple of those 2 values, and then we return it. So that's how we hash the state of the game, essentially. Otherwise, it was pretty straightforward to program. I think it was one of the simpler challenges to solve. So I solved it quite quickly, and in the end we got the answer. Next one was day 23. So for day 23, we again play with our crab. But this time, rules of the game are different. Essentially, you need to arrange, you have a number of cups and you need to arrange them clockwise. You get initial assignment as this one number. Essentially, each every digit is a cup value, cup label, and they are all arranged in a circle. Sample input is 3, 2, 4, 1, 5, and then if you go clockwise around the circle from the first cup, the cups would be labeled 3, 2, 4, 1, and 5, and then back to 3 again. Before the grab starts, it will designate the first cup in your list as the current cup. The grab is then going to do 100 moves. Each move, the grab does the following action. The grab picks up the 3 cups that are immediately clockwise of the current cup. So we start 3 is our current cup. Here is actually the, suppose your cup labeling was 3, 8, 9, 1, 2, 5, 4, 6, 7. So first cup, current cup is 3. Then we take 8, 9, and 1 as 3 cups that we pick up. They're removed from the circle. Cup spacing is adjusted as necessary to maintain the circle. The grab selects the destination cup. The cup with the label equal to the current cup label minus 1. If no such cup exists, it subtracts 1 until it reaches final cup. And if there is no, if you go essentially below 1, then we wrap around and we go again to the top cup. The grab places the cups to just pick up so that they're immediately clockwise of the destination cup. And the grab selects a new cup, the cup which is immediately clockwise of the current cup. So essentially we start with 3, we pick up 8, 9, and 1. Destination is 3 minus 1, 2. So it's located here. We put those cups after 2. 2 is now after 3, so it's next current cup. We pick up 8, 9, 1 again. Next destination after 2 is 1, but it's picked up. So we need to wrap around. We wrap around. We get to 9, it's picked up. 8 is picked up. 7 is not picked up. So destination is 7. And then we essentially place those cups after 7. Now, because it's a circle, we have 3, 2, then those were picked up. So then we have 5, 4, 6, 7. And then we place them. That continues, and in the end, we have this as a final after 100 moves, and we need just to return a number. Starting after the cup labeled 1, we go clockwise and we collect labels until we know the numbers that we need to return. So if we call this thing, we see that it also runs very fast. That's my answer. What's about implementation? So here it was a bit interesting. At first, I start with actually modeling the whole thing via this data structure, where I used a vector of labels, where each label is U32. I had a current index and current label, and I had a staging area where I pick up the cups. And then I programmed the whole thing where I parsed it. I then executed a move. So there is a bunch of logic to like rotate stuff. I noticed that we always maintain the invariant that our current cup doesn't change position. So if you look at those turns, you see that 3 is at the top, 2 is second, 5 is then third, etc. So that's kind of the invariant I used. And that's essentially what I'm doing here. So we have some helpers for returning index range so that we wrap around the list. For example, we can get an index by label of the cup so that we know, for example, where the destination cup is located. And when we execute the move, we essentially take the current label, we pick up the cups, where pick up is using this index range helper to select after the current index the one that is 1 after and then 2 and 3, so like 3 cups after the current cup. For each of those indexes, we put them into staging area. Then we remove them from data, and then we restore invariant. So restore invariant is the key here, because restore invariant essentially rotates data buffer in such a way that current index always points to the element with the current label. So that's the invariant I was talking about. That allows us to maintain consistent assignments throughout our algorithm. And here, essentially, I just use functions rotate left and rotate right that are already provided on slices in Rust. And I just calculate my rotation as the difference between new current index and minus self current index, essentially. Then, so yeah, once we picked stuff up, we moved those 3 cups into the staging area. Then we find destination labels. So using this algorithm where we check if we have it in our picked up cups, we continue to select -1 until we reach 0. If we reach 0, then we go to the maximum label and we continue with the algorithm until we found some number that is free. Then we get the index of the destination that we call self-place. Place figures out destination index +1 till destination index +3. It enumerates them, and then it essentially, if placement index is larger than self-data length, then we just push it in the end of our vector. Otherwise, we insert it at the placement index, and then we restore invariant again. So that current index again points to current label element, and our arrangement is stable. After that, we just need to select a new current assignment. So we call next current, where we just increment index by 1. Yeah, increment index is another helper function that I use to also implement index range, for example, where I'm just using modular arithmetic. So that was my solution for the first task, and I actually knew that there are simpler ways to solve it, but I thought, okay, probably we will be asked to change the rules of the game. So for example, rotations will be performed somehow differently or something like that. So that's what was my expectation, and that's why I decided to model everything precisely. That turned out to be not the optimal solution, because when I solved the first part, the second part was essentially the same, but you get 1 million cups in total and you need to perform 10 million moves. So then my solution was too slow for that. Then I thought about solution I already thought when I was reading the first part, that I probably can model that as linked list, but doing linked lists in Rust is pretty tough. So instead of doing linked list, I went here and used an old imperative programming trick, where in essence you have an array of things and you use indexes to things as essentially elements of the array, and values under each index is the value of the next element. And since next element value is next element's index, you can essentially work the linked list by just going from one index to another, looking at the value, using it as the next index, etc., etc. So for example, with our testing buffer, we got this scene. Those are arrangement of the cups that are arranged in a circle. If you look, we can then put at under index 0, we put 3. This is like our current thing. Then under index 1, we put something that is after. Then under index 3, we put something that is follows 3. So 8 follows 3 in our arrangement. So here we put 8. 8 is followed by 9. So under index 8, we put 9. 9 is followed by 1. So after 9, we put 1. 1 is followed by 2. So after 1, we put 2. And 2 is followed by 5, so under 2 we put 5, etc. So essentially we get like a different arrangement of elements, but it expresses our next after this one relation using indexes and values as tuples in essence. It allows us to save memory, and it allows us to do very quick movements throughout this linked list. It also allows us to easily modify it. So for example, we let's probably just go through the algorithm because then it's easier. So yeah, I just create this array. Now, one important thing that I actually experienced Stack Overflow when I used cargo test on that. So it was running just fine, but when I from my REPL, from cargo run release, but when I did cargo test, it failed. And this is because this array contains 1 million elements. So it's pretty big. It's essentially 8 megabytes, and which meant that it overflows our stack when we try to run multiple threads from the same process. And that's why I needed to use static mute here. So essentially put it in my program itself, in the data portion of the program, not on the stack, which allows me then to not have stack overflows when I run tests. there is a link to Stack Overflow article about that. So you can actually, Stack Overflow thing, but you can read it here. And of course, we have total caps 1 million. Here we need 1 million plus 1 because we use the 0 element as our current cap arrangement. So then parsing is pretty straightforward. We just put stuff there. We then select the current cap is the value of the first position. We add our initial caps. Caps is just a vector of the integers we got as original entry, essentially. We then we use Windows function for the slice of this caps thing, and we got previous and next cap labels for each of those, essentially. Then in our ring array, we use previous index, we set it to the value of next. So implementing this exact arrangement I was talking about. And of course, if we are not having that, then this is unreachable, so we don't need to actually process it. Then for remaining caps, we add them using the same logic, but here previous and next are of course no longer references to elements in a slice. They are just numbers that we increment manually until we reach our total caps. And in the end, we need to close the circle, so the last cap will be referenced to our current element, and that's it. Then for each round in our 10 million rounds, we pick up 3 caps. So first cap that we pick up is the cap after the current cap, which means we take the value from the current cap index. We then go by using this value as an index, and that's our value of the cap after the current cap. Then we can use it to look up the next one cap after that, and then the next cap after that we look up by the value we got here using it as an index. So those are 3 caps that we picked up. Next, we need to find the destination. So here we implement similar algorithm where we just find the destination index, essentially. At first, we start with current cap minus 1. If it's one of the numbers we just picked up, if it's our current cap, or if it's 0. If it's 0, then we set it to the largest value we know, and we repeat the loop until we find that it's really free and we can use it as destination. Otherwise, we just decrement it. Now, having current cap, having 3 caps picked up, and having our destination, we need to go from this arrangement where we have current cap pointing to pick 1, pick 2, pick 3, and then some cap after we pick 3. Then some caps in between, then our destination pointing to the cap after destination. We need to go essentially to current pointing to this cap after pick 3. And our destination pointing to pick 1, pick 2, pick 3, and pick 3 pointing to after destination. Now, because of the way our ring array is arranged, it means that essentially we just need to change this current value under the current caps index to be after pick 3, that we can find very easily. By just looking at what we have currently on the index, which is pick 3. And for destination, we just need to change that value to point to pick 1. Pick 1 already points to pick 2, pick 2 already points to pick 3, and pick 3 need to start pointing to after destination. That's it. So first we redirect the current to after pick 3. This is our current cap value. We set it to the value that is under index pick 3. And then we place picks between destination and after destination. You can actually use swap function here to swap those, but when I tested it, it was slower for some reason than just doing it manually. So I just do a manual swap where I have after destination as a local variable. I use destination as my index. I get the value there, so that's the label of the cap after destination. Then destination value becomes pick 1, so destination now points to the first picked cap. Pick 3 becomes after destination, so pointing to the cap that was previously after destination. And then new current cap is just the cap that current cap is pointing to now, essentially. In the end, the answer is changed. We just need to select the cap that is after 1 and the cap next to it. So, and we need to multiply their values. So that is easy to select. Cap after 1 is the value under index 1. And cap after that is the cap as the value under index that we just got when we did ring 1, essentially. We multiply them and we get our answer. So now, if we do that, it takes a bit more time, but you can see that it performs still under second. So I think it's pretty good performance. And of course, if we will try to do the same with our original solution with vector, where we actually rotate and move elements around, that will not terminate soon. So that was significant optimization improvement. Now let's talk about day 24. Oh yeah, day 24 I think was one of my favorite days, because in essence this is Game of Life again. So it's the third time we need to implement Game of Life, but this time we use hexagonal tile floor. So first we need to learn how to walk those tiles. Essentially we get coordinates where, sorry, not coordinates, it's more like turtle graphics where you get like instructions where to step next. We have east, southeast, southwest, west, northwest, and northeast. There are no delimiters, so we get like one string. Then all tiles in the tile floor start as white and can be flipped to black. And we essentially got a number of directions. When we arrive at some tile, we flip it. So if it was white, it becomes black. If it was black, it becomes white. And we repeat it for each of those directions we got. And in the end, we just need to calculate the number of tiles that are now black. Of course, our input is way larger, so we got 431 lines here. And the first thing, since our tiles are hexagonal, we need to somehow emulate hex grid. I figured out that there will be some trick and I wanted to just solve it. So I went here and I looked at possible coordinate systems for hexagonal grids. This is pretty cool website which mentions how to implement it efficiently. The most simple thing to implement was those cube coordinates. So that's how it looks. And here you can play with it interactively. So we start with everything 0, 0, 0, and then for each direction we either add or when we move to each of those hexagonal directions, so east, west, south, west, southeast, north, east, northwest, we change 2 of 3 coordinates essentially, and we either add one or subtract one from each of those. And here you can see how it works. So x's are added on this axis and subtract on this axis, and the same with y's and z's for different directions. So that was pretty simple to implement. I just created a tuple for coordinates and hash map with booleans. Actually, I could have also just set it to hash set, but I was not sure if I need to track which tiles are present or not. And which ones are flipped, because then you actually need to have bool and entry in hash map as like 2 things here, but I guess in the end hash set would have worked as well. And you get a pass, which is a vector of directions, and direction can be any of those 6 possibilities we got. First thing, of course, is parsing directions. Thankfully, it's quite easy. So we know that if it's east to west, then we just push it there. We need to track offset here. If it's south, offset will be 2 instead of 1, because we need to parse next letter as well, same with north, but otherwise it's pretty straightforward. In the end, we return a vector of directions. Then we need to be able to step around, so we just follow rules from this scene, essentially, where we, if we go east, we add 1 plus 2x, and we subtract 1 from y, and etc. for all other directions, essentially. We just follow those rules. Then we have a function flip, which just follows the path, calling step on each of the coordinates we got. And in the end, it just, if there is an entry for the coordinates that we reached, we insert false and then we flip it. If there were something already there, we just flip it without inserting false. True means black, false means white here. So that essentially, and then we just need to count black tiles, which will be, we go through our hash map of tiles and we filter them only taking black ones, and then we call count function, and in the end, that's our result. So when executed, we got the answer very quickly, and that answer is correct. Oops. Then part 2 is essentially we need to implement game of life on that. So for any black tile with 0 or more than 2 black tiles immediately adjacent to it, it's flipped to white. Any white tile with exactly 2 black tiles immediately adjacent to it is flipped to black. It's very similar to typical game of lives rules, so we just need to implement that. Overall, we already have a function getArrangement that creates a path, so we can use that. And then we just need to implement a function advance with the counter of moves. We need to again track our currently occupied zone, so tiles that we actually expanding or collapsing, because we don't have a limit on the borders of the grid. So that's why we have this function complement that takes immutable reference to our hash map of tiles. And then it gets max x, y, and z values for each of the possible directions. And then it just checks if we don't have some key in those ranges. We just add it with our tile by default flip to be white, so false. So we set previous value to the current tiles. We complement them. And then we have a delta array of neighbors, essentially. So each tile has 6 possible neighbors because we are working with hexagons. And those are coordinate offsets for each of those. We also have a function add that essentially adds 2 coordinates together, allowing us to get neighbors. Then for each move, we initialize next as empty hash map. For each coordinates in our previous tile arrangement, we use mutable neighbors vector, which we set to capacity 6, so we don't need to reallocate it every time. We remove everything from it. For each delta, we add the neighbor there. And yeah, essentially, we push them to neighbors. We count if they are black. Then we can count the number of black neighbors. So if the neighbor is present and is black, we add 1 to our black neighbor count. Otherwise, we don't change it. If neighbor is not present, we insert it into our new tile map. And then we just implement the rules. So if black neighbors is equal to 0 or more than 2, we switch to white. If tile is white but black neighbors is 2, we switch to black. Otherwise, we don't change the tile color. And then after doing that for all our coordinates, we reassign and we now use next as the previous one. And we execute next move. In the end, we just return the value of the previous hash map. So that's essentially game of life on hexagonal grid. And then we just again need to count black tiles. So we got our answer, and we can see that this answer is correct. So that brings us to the last day of Advent of Code, day 25. So this day was different because we only got one part of the puzzle here, which is essentially, it looks like a typical encryption thing, but very, very simplified. We get two numbers which are called public keys, and we need to figure out loop numbers. Then we need to multiply one public key by the loop number. Sorry, I'm already forgetting what exactly was rules. So yeah, set the value to itself multiplied by the subject number, set the value to the reminder after dividing the value by 20, 20, 12, 27. So we got like two public keys. We then execute this loop size number of times. We got encryption keys. These should match for both of those public keys, essentially, combined with the loop length. And then we, I think, just need to return encryption key. Yes. So we got public keys as input, and then you essentially need to implement the algorithm they described here, which I did. So at first, I just use this find encryption key. We first define loop sizes. Then you call this transform procedure using loop size and public keys. And then you make sure that both candidates you got are exactly the same, and then you return the first one of them. So for find loop size, you start with loop size 1 for both of those. And then you call transform with number 7 and loop size. And until it's not equal to public key, you increase the loop size. In the end, you just return both loop sizes. And transform with this procedure we were talking about. So you multiply by result by subject, and then you find a reminder when you divide it by 20, 20, 12, 27. Now, when I first ran it like that, it was too slow, so you need to optimize it. And that's why I have function find encryption key simple, where essentially I only find one loop size, and instead of resetting it for each of the possible loop sizes, I continue to multiply, increasing my loop size. So that was very straightforward optimization. I just copied essentially this function. I took the first part here. I then figured that I'm resetting loop size all the time. Instead, I'm just increasing it here, and then I calculate it in one expression here for my result until my result is not equal to public key 2. And then I just need to call transform only once, because with both transforms of public key 1 with loop size 2 and public key 2 with loop size 1, I will get the same result, so I don't need to do it twice. That's why I only need one loop size. I can optimize slightly how I calculate it, and that's sufficient to solve the last day of advent of code. So we got this answer, and that's it. Then I needed to have 49 stars to get the last star, which means I needed to solve day 20, the days that I didn't solve before. So that's where I went back and I started solving it. As you may remember, day 20 was you get those tiles that you need to arrange according to rules that edges should match. And then you need to create this picture from them. And then you need to remove borders, arrange the picture, and find C monster according to this pattern. And then you need to calculate the amount of hashes that are not part of C monster. That's the day 20. And I solved the first part by using heuristics that we probably don't need to have, like on the borders, in the corners, we don't have matching borders with anything else. So then I could find corners, and then I could multiply the IDs of tiles in the corners together, and that was the answer for the first part. But I never finished actually arranging the map itself and finding the monster. So I needed to go back here, which I did. And there's a bunch of things here. My first attempt was trying to solve it with mean conflicts algorithm, but in the end it didn't work. It was not a good match for mean conflicts, and instead I decided to switch to backtracking. In essence, I implemented backtracking algorithm. In backtracking, you go from empty assignment and then add one assignment for each of the variables you have. And you backtrack if something stops matching, so if you cannot find any more assignments there. In this case, we know that we can precede it with our corner coordinates. So we know that we can start from a corner and use one of those things that we got as corners as first tile, and then we can just go through the possible transformations. That's why my precede assignment is. I also knew that I probably won't be able to optimize the algorithm very well, and I didn't want to spend too much time on that. So what I did, I just ran it multiple times until I got one of those working. That's when I got the A20 solved, where I got those tiles. And that's why I was able to, for my following passes, just put the correct corner in correct orientation as the next tile there, as preceded. And I did the same for sample. Then I have unassigned cells, where I just put everything that is not in preceded assignment. And unassigned tile IDs, same thing. And then I call backtrack inner. Backtrack inner takes all possible transformations. It takes the first unassigned cell. And then corners has already been inferred. We just need to look at those that are not yet assigned. So if this is a corner coordinate, then we just look at the corners that are not yet assigned as possible tile IDs. Or we just look at the possible matching neighbors. So since each edge of each tile is unique, we could convert it to numbers, which I did, to find out corners on my previous attempt to solve the A20. So I then can just look at the tiles that have the edge with matching number. And then I can use it as entering my possible tile IDs. If I don't find anything, I know that my backtracking failed, so I need to return none. And otherwise, I just use it to seed my possible tile IDs. Then for each possible tile ID, I get the tile and I try to apply all transformations until I find some assignment that matches. So I call backtracking with the new assignment, and if it returns me correct result, I return it. Otherwise, I put the candidate hash, so the hash of the assignment I just tried, into scene assignment, so I don't try it again, and I try a next transformation or next tile ID. In essence, it ends up finding the assignment I wanted to. And here, when I call day 20 part 2, we will see now the image we got after running it. Since I precede stuff, it executes very quickly. Otherwise, it would have been quite slow. In essence, if you just use it with like different input, you need to run it multiple times until you got something convergent. If it converges very quickly. If it doesn't converge, it will try to search until it exhausts all possibilities, so it can take a very long time. So that's why I just need to start it. If it runs for more than a second, you kill it, you start it again, you do it multiple times, and eventually you will get your correct orientation of the first tile. And then, of course, if you start with that, then it will converge immediately every time. That was, though, not everything you need to do in day 20. Next thing that you needed to do is actually find monsters. So for that, I implemented this function find monster. So monster has this particular pattern, but like empty places here can be either hashes or they can be dots. So I essentially needed to convert monster to my to a vector of optional characters, and I implemented function match row, checks that we are matching, and then I just go through all possible coordinates trying to apply those 3 rows and see if we are matching. Then I return a vector of monster coordinates that matched. Then after I found monsters, I know that I have 15 caches inside the monster itself. So I multiply 15 by the monster length, and then I calculate the number of hashes in the whole image, and then my result is just all hashes minus monster hashes. And here you see it was calculated as 2155, which was the correct answer. So I solved it here, and then when I returned to day 25, it essentially said that we can check on our deposit, and that's the page you see in the end. So talking about that we finished the advent of code, and then of course we have this beautiful picture with the sea monster here, and we got this little galaxy flying around, or like a thunderstorm, not sure what it is. And there are islands, so yeah, quite cool. In closing thoughts, that was a very exciting event of code. For me, it was the first time I actually solved everything. And of course, solving it in Rust was quite challenging at times, but also it improved my speed of writing Rust code tremendously. I'm now way faster when I write it, and I learned a bunch of new library functions, and I also learned a bunch of new computer science theory, really, or got a reminder of some of the topics. So it was very interesting experience. I will definitely do it next year. I will probably do it in Julia next year, and I probably won't be streaming it live, at least not all days, because it was quite overwhelming to try to stream everything. But I will definitely do some streaming anyways, and I will be posting my solutions as usual. I will put a link to the code as usual in the description, so you can check those solutions yourselves. We have this nice Replit interface which you can run and you can play with them. Of course, a lot of solutions can still be improved. I typically, after solving the day, I went to Reddit and I saw other people solving stuff very simpler in some situations. For example, in one of the first days, you just needed to convert a number to binary. Instead, it implemented the whole recursive thing, but it worked. Same was with day 10. We went for a very customized solution in the end, but you could have actually, if I persevered with dynamic programming and just figured out that I can start from the back instead of from the front of the adapters arrangement, that would have been way simpler. But in any case, achievement unlocked. I will continue with my typical streams later this week. I think I will do another stream on Saturday. We will be returning back to more typical programming, so probably we'll do a bit more audio adventures in Rust. And thank you so much for watching. See you next time.